we start with first a simple 2 approximation for first fit. Then we'll see a 7 by 4 approximation for first fit. And at the end, we'll see 1.7 asymptotic approximation for first fit. So that factor 2 comes from a simple fact that if I take any two consecutive bins in first fit, the weight is at least 1. Or we already saw another property. So there is this property that at most one first fit bin has load at most half. We proved in the previous lecture. So using this property, we are defining this weight function. For any item of size x, we'll use the weight to be 2 times x. And then, as we are saying that all bins except one has load at least half, that means all these bins, if we look at their total weight, the total size of items are more than half. So 2 times xi is strictly more than 1. And that means if I look at each bin except the only one bin which has load less than equal to half, all other bins are at least weight 1. So we can get this inequality that total weight of all items is more than FFI minus 1. And now we have to also charge the optimal side. Each feasible bin has total size at most 1 because they're packed in a bin of size 1. So total weight of their bin, their size is 2 times sum of xi is less than 2 times 1, which is 2. And that's why if I look at all the bins, all the items in the optimal packing, total weight of these items are just 2 times the number of optimal bins. At most the 2 times the number of optimal bins. So we get this upper bound on the weights, and this two together gives us total number of bins for first fit is less than equal to 2 times opti plus 1. And with a more careful analysis, actually, you can show it 2 times opti minus 1. So this shows the simplest weight functions. Now, we'll improve it further. So just remember the 4 properties that we showed earlier. And one property we already used, that at most one first fit bin has load less than equal to half. Then these 2 properties are also interesting, and that will be crucial in the next proof, that there is at most one singleton bin that contains an item of size less than half. All other singleton bins will have items which are strictly more than half. And for multi-item bins which contain at least 2 items, all the bins except probably one, the load is more than 2/3. So now 7 by 4 appears kind of automatically. So we know that all but at most one multi-item bin has load strictly more than 2/3. So if I put the weight function to be Wx equal to 3 by 2x, then all such bins have weight 3 by 2 times 2/3 at least 1. So we are fine. So our goal is basically to show all the bins produced by our algorithm, most of them except some constant number of bins have weight 1. So what are the problematic bins? So multi-item bins we are done except one bin. Now we take singleton bins. Except one bins, all other bins have load more than half. But if it is just, let's say, half plus epsilon, total weight of that item becomes 3 by 2 times roughly half, which is 3/4, which is not getting 1. So if a bin in first fit is having half plus epsilon items, I still want to make sure the bin receives weight 1. So for that, we do a local repairment. We add a 1/4 extra bonus for those large items. So if the item size is more than half, we put extra 1/4 bonus. And then we're done. Because then in the first fit side, if we look at any multi-item bin except one bin, every other bin we are paying at least 1. And singleton bins except size at most half, all other bins have size more than half, and then we use a bonus and we're again getting another extra. We are again getting the weight of the bin to be 1. So except 2 bins, all other bins are weight 1. So ff minus I minus 2, the number of bins by first fit minus 2 is upper bounded by the weight of all items. And offside, it's also easy to see that a feasible bin will have the total weight is 3 by 2 times 1, total size is at most 1. And it can have at most one large item, which can give another 1/4 extra profit, extra bonus, and total that will give us 7 by 4. And these two together is giving us that first fit is less than or equal to 7 by 4 opt plus 2. So now think a bit, how can we go beyond 7 by 4? And for that, we have to look at the properties of first fit, these 4 properties again carefully. So maybe you can pause the video for 1 or 2 minutes and think, what is, if we choose some other weight functions, let's say some lambda x, where lambda is less than 3 by 2, as we're using in 7 by 4 bound, what will be the problem? And once you're done, then you can continue with the video. Okay, so let's see. To beat 7 by 4, what should we do? Let's say we try some lambda x, where lambda is less than 3 by 2 and more than 1. And then for some items, we need to add some bonus. We already saw for x greater than half, we had to add some bonus. Now let's look at one bin, which is multi-item bin B, and the load is more than 2/3, we know. But let's say it's just 2/3 plus epsilon. And then what happens is, if we look at just 2/3 plus epsilon, and the lambda we chose is much smaller than 3 by 2, then the load of the bin is already less than 1, strictly less than 1. So we want to use some bonus to pay for this extra, the deficit that we are having. Now let's look at the later bin, some other multi-item bin C, and there are 2 items, let's call it X and Y. And we know that we could not put X in this bin B, neither Y. And let's say this gap region is R, which was unused in this bin B. Then X is at least R and Y is also at least R. This is the property, the blocking property we already saw earlier. So we are trying to use we'll try to give some bonus to X and Y to pay for this bin B. This is a very nice idea because, I mean, if we just look at the items in B, we don't have any size guarantee here. So there can be more than R, less than R, all these things can happen for these items. So we are charging items in some other bins, later bin, and that will be quite helpful as we see. So let's look at the case if the bin B has load 1 minus R, and we know this load is at least 2/3, so it's more than 2/3, so R is strictly less than or equal to 1/3. And as I mentioned, if the next item X and Y we're not able to pack it, then the size is more than R. So what is the amount of deficit we are having? So this bin has load 1 minus R times lambda is the profit we are getting from the lambda X function. But then we need at least one total weight for the bin. So 1 minus this part is the deficit. And I'm using plus because if the deficit already lambda times 1 minus R is crossing 1, we are fine. Then there is no deficit. Otherwise, there is a deficit. And we know C has at least 2 items which are size more than R. And we want to use these 2 items to pay for the deficit. Now here, if we see, the property we have is X is more than R. And also we know 1/3 is strictly more than R. So R is less than or equal to minimum of X comma 1/3. We just put that value here, R, and then divide by 2 because there are 2 items going to pay them. So if we do that, then we'll see this is true for any multi-item bin C. If we have these items X and Y, there are 2 items, we can use their bonus. V lambda is the bonus function, and the lambda times load B is the regular weight coming from the load of B. That is at least 1, and we are done. So it will be true for any lambda. Now the question is what lambda to choose. But if we look at this function itself, we see some properties that if we define this T lambda to be 1 minus 1 by lambda, then we'll see that if I look at the bonus function, it looks like at till T lambda, the bonus is 0. And then till 1/3, so I'm calling it the V lambda X. This is the X value. And this is 1/3. Maybe I'll use, yeah. So here there's an increment by lambda by 2 times X minus T lambda. And then there is again some kind of plateau like this, which is half minus lambda by 3. So what does it mean? There are 2 breakpoints kind of. One is T lambda and 1/3 X. So if x is less than t lambda, then you can see that load of B is 1 minus 1 minus 1 by lambda, which is 1 by lambda. So already the lambda function directly pays for weight 1. So we don't need to put extra bonus on such small x. So for this portion, we can put just bonus to be 0. And then it is increasing. But once it reaches 1/3, we already have sufficient amount of bonus to pay for. So we don't need extra bonus. Remember, if we give extra bonus, it will help the algorithm side, but also it will create problem in the feasible bin capacity. That value will increase. So we want to keep the bonus as minimum as possible and still satisfy this constraint. So there is a plateau here. Now, are we done? There is one more thing that we took care of the multi-item bin, but the single item bin is still a problem. So if I look at an item of size half plus epsilon, previous case we added this extra 1/4 bonus. We need to add something similar. So if we look at now, from the size we'll get half times lambda roughly the bonus, the weight. And if you look at the function for x more than 1/3, we give bonus to be half minus lambda by 3. That will give us half plus lambda by 6, but we need 1. So we add another extra bonus of half minus lambda by 6, and that is the function. So final function we give is this function, that lambda x, then v lambda x is the bonus we add to all items. And if the item is more than half, we add another extra u lambda bonus. And we'll see that for any lambda between this value, this function is good enough, and all the bins are well paid except 3. So think why 3? And we'll see later, but it's, I mean, intuitively, one thing is all multi-item bins are fine except probably one, which has load less than 2/3. All singleton bins are fine, which have load more than half. So only one bin is there, which has load less than half. And what is the third bin? And there this charging argument comes. So we are basically charging one item to the next item. So if you think of the last item in this chain, we'll not be able to charge it. So again, see the property in some time. Now, for any lambda it is true. So what lambda should we choose? And some intuitive idea will give that what is the right lambda, and then we'll prove it works. So remember, the goal of lambda, this is, I mean, we are fine with any lambda, which will satisfy, I mean, with this function, which will satisfy the algorithmic side, will pay at least 1. Now we have to show none of the feasible bins have large weights. And for that, there are these two problematic pairs. So half plus epsilon anyway is a problematic one because it has a lot of bonus. We want to put them. And then one option is we can add a half minus epsilon. Now, if we have half minus epsilon, the bonus we get, total value we get is half plus lambda by 6. We get lambda by 2 from the regular weight, lambda times half. And then if you look at the function, we get half minus lambda by 3 here. So plus half minus lambda by 3, that gives us this function. So we need at least, this weight becomes at least 1, this becomes weight 1, and this becomes weight lambda by 6 plus half. So at least this will be the weight of a feasible bin. On the other hand, if we take the other triple, which is 1/3 plus epsilon and 1/6 minus 2 epsilon. The reason it's also problematic in this is because we know that after 1/3 plus epsilon, relatively the bonus increase and then it gets a plateau. So it's better to just stop there. And then we get the total weight to be 1 for this item. For 1/3, we get lambda by 3 plus half minus lambda by 3. And for 1/6, we get lambda by 6 plus, there is no bonus because it's 1/6. So total we get, did I make some calculation mistakes? So half gets 1, lambda by 3 plus half minus lambda by 3. Yes, there was a calculation mistake. So if I look at this, the weight is 1. If I look at 1/3 plus epsilon, there is lambda by 3 from regular lambda times x. And then this is the bonus, half minus lambda by 3. And if we look at 1/6 minus 2 epsilon, roughly we get lambda by 6 from the weight. And then there is a bonus, which is lambda by 2 times 1 minus 6 minus t lambda. And then if we expand, we get t lambda is 1 minus 1 by lambda. And then if we do these calculations, we'll find the value to be 2 minus lambda by 4. So in one case, we are getting it is at least 3 by 2 plus lambda by 6. In other case, we are getting at least 2 minus lambda by 4. So intuitively, if we make lambda to be smaller, then the weight becomes larger in this case, because what happens is then the items start getting bonus for much smaller values. So 1/6 gets more bonus, and 1/3 gets more bonus, and that creates a problem. On the other hand, if we make lambda to be too large, then the slope is high, and then half minus epsilon gets more bonus, and then also it's a problem. So higher lambda means more value here, lower lambda means more value here. We try to balance them, and the balance happens when it's 6 by 5. And that will, if I put this value 6 by 5 here or here as lambda, we'll get it 17 by 10. And we'll see formal proof, but that's the intuition why the final function looks like this. So now it is no more a magic. Initially, if you look at this function, it will look like a magic. But now what we see, we have chosen this lambda to be 6 by 5 to balance. And this bonus function is just from this function, we get 0, lambda by 2 times x minus t lambda. So t lambda is now 1 minus 1 by lambda, which is 1/6. That's the breaking point now, 1/6. And this lambda by 3, it becomes half minus 6 by 5, so 1 by 10. No, 6, yeah, 2 by 5. So that's what we are getting here. If we just plug in those values of lambda and t lambda, this is the exact function we get. And this 2/5 was the extra value we put for the singleton items, the large items. So this function will look like this. And this kind of explains why there is a breakpoint here, why there is a breakpoint at 1/3, why there is a jump at half. The reason at jump, because if I look at half minus epsilon and half plus epsilon, they are quite different. If I put more weight, I mean, I have to put this weight of 1 for half plus epsilon items. But if I put same weight for half minus epsilon, then two items which have size half minus epsilon, they will fit in a bin. So the total weight will cross, I mean, will reach 2. To avoid that, there is a discontinuity here. So this function is no more magical, but the first time if you see the function, it looks magical. So the message is, for weight functions, you have to study the properties of this algorithm, and then it will be a natural consequence. So as I mentioned here, this 6 by 5 slope was chosen because of this two dichotomous example. In one case, we have a half pair, half plus epsilon, half minus epsilon. In other case, we have nearly half, 1/3, and 1/6 triples, and the balance. And as I mentioned, if already is 1/6, then that's already it is enough to have this jump at 1/6, because then you get enough bonus from the points which are coming later. And at 1/3, we already get enough bonus, so we don't need to add more bonus. So if you look at this is the baseline, there is a different function in this region. Otherwise, the bonus is always a constant. It's 1/10, 2/5. So some bonus is there, but the jump is constant. So we got the intuition behind the function. Now just to end the formal proof. So first we show that every feasible item has load less than 17 by 10 or 1.7. So already we saw that the load coming from this lambda x, lambda is 6 by 5, already 6 by 5, because total size is at post 1. So we have to show the bonus does not exceed half. There are two simple cases. if there is no item more than half size, then it's easy. Because if we look at the function here, we see that maximum bonus an item which is size less than half can attain is 1/10. And how many such items can be there? If we already have no items more than half, and the positive bonus starts from 1/6, so there can be at most 5 items, and each of them can contribute at most 1/10 bonus. Total bonus is at most half. So this is fine. The other case is more intricate. If there is an item which is crossing half, then already that large item will give you 2/5 bonus, as we see here. It's a 2/5 bonus. But then we can conclude that if I look at such bins, then there are two cases. The remaining items are anyway size half, and there can be one or two items with positive bonus. If there is only one item with positive bonus, we know the bonus is at most 1/10. The sum is again less than half. But sum of this 2/5 plus 1/10 is less than half. Otherwise, if you have multiple items which have positive bonus, as the total size is less than half, and we know their size is at least 1/6, we know there are exactly two items and their sizes are between 1/6 and 1/3. And this is the bonus function for those regime, if you remember. And then the sum of their total bonus is just the sum of, I mean, if it's a linear function, you are adding for x and y, if there are two items, total size is z, and z is at most half. So we get an upper bound of 1/10, which will again give you a 17/10 upper bound on the total weight of any bin. And let's repeat once more why it is true for first fit. Almost all bins are paying for 1. So we now have this function 6/5 load, and we have this bonus function v. This bonus is basically the bonus before the singleton surcharge. So it's multi-item bins we are talking about. So in that case, if already load is more than 5/6, we're done. Total 6/5 times load is already sufficient. Otherwise, if the load is 5/6 minus delta, it's slightly smaller quantity, then every item in C is larger than 1/6 plus delta, and their charge is 3/5 delta. If we look at this function, if the size of x is 1/6 plus delta, then this is 3/5 delta. That's what we get. From two items, we get 6/5 delta, and this sums to 1. So all bins are 1, at least weight 1, except 3 bins. Remember, there is one singleton bin which can have weight at most half. There are 1 multi-item bins which can have load at most 2/3. And third bin is basically in the charging, we are taking a bin B1. We look at the all multi-item bins, and we can charge B1 to the next bin B2, which has 2 items, which we could not put here, and continue. So the last bin, we cannot charge any more next bin for its weight. So it can still have less than 1. There is no later donor. So this third bin is also a problematic bin. So except these 3 bins, all other bins have weight 1. And this together shows a guarantee of 17/10 opt plus 3. So you already get 17/10 asymptotic approximation. Now this function I chose is slightly simpler function compared to the original function by Ullman and others, because that they give slightly better bounds, but I think it's more intuitive to understand this function, and it gives the same bound. And if you analyze more carefully, then you can get even a better bound of 1.7 opt floor. So this concludes the analysis of first fit. I'll also briefly mention about the weight function from a viewpoint of primal dual. So for that, I need to define something called configuration LP. It's an advanced addendum, so you can skip it if you want. But I think it's good to have this viewpoint that one can use a dual fitting viewpoint to analyze the same problem, same algorithm. So first, let us define what is a configuration. Configuration is a feasible bin pattern where total subset of items that size is at most 1. So think of these 3 items, 3/5, 2/5, and 3/10. Then if I pack them, I can pack item 1 and item 2 or item 1 and item 3 is a feasible configuration. But if I take 1, 2, 3, total sum is crossing 1, so it's not a feasible configuration. Now I can define a variable for each of these configurations. And then that will lead to this LP called configuration LP. What is this LP saying? It is saying that I want to minimize the number of bins. So each XC is 1 if I select the corresponding configuration or corresponding bin. And my goal is to pack all items or to cover all items. So I need to look at any item I in the input and look at all the configurations where this item is present. At least one such configuration should be covered, should be taken. Say, so for that, x is equal to 1 and we are fine. So in fact, we need strictly 1 for our problem. But if it is a covering constraint, so it's more than or equal to 1, I can, if there are multiple configurations selected which has the same item, we can just choose any one of them and put the item there. And then if you write the dual of this configuration LP, you will find this one, this dual LP, which intuitively says that, okay, you are putting some weights on each of these items. And then what you the constraint becomes is, if you look at any feasible configuration, the total weights of these items are less than or equal to 1. And you have to maximize the total weight. You have to find some Zi such that this is maximized under this constraint. Now, if you look at this is like dual function, like weight function. In weight function, what we are trying to do is we are putting some weights, like Zi we are putting here. We are also putting some weights on items there. So if I choose this weight function WSI that we have chosen earlier and divide by U, in this case 1.7 in first fit, then we get this Zi. The point is a dual feasible solution. Why? If I look at the sum of Zi here, that is exactly equal to 1 by U times sum of WSI. But from the property of weight function, we showed this is at most U, the total sum is less than or equal to 1. So it's a dual feasible solution, and that's already sufficient. Why? So if I look at sum of WSI, total weights, intuitively what we showed, it's roughly like number of bins produced by the algorithm, except some constant number of bins. So that's an upper bound on opt. So this is just a number line, and this part is the value of the primal LP. We're trying to minimize, and this is the values for feasible duals. And we know from strong duality, this LP star is same, the optimal configuration LP, primal value, and the dual value, they are same. Now we know this sum of WSI is an upper bound on opt because roughly like it's like AI, which is the number of bins produced by our algorithm. But if I divide by U, then this quantity is a dual feasible solution. So it's somewhere lying here. But if that happens, then Wi by U is a dual feasible, so it's less than or equal to the dual optimal, because optimal is the maximum value of the dual. But then that's also equal to the optimal value of the primal, which is less than or equal to the optimal integral value, where the number of bins we have packed it integrally. And from the algorithmic side, if we show some bound like L times AI minus beta by U, this Wi is more than L times AI minus beta, then this together gives us the same guarantee. So it is called dual fitting. You're taking a dual and then you're taking a solution and then dividing by some value such that it fits the dual, and then use that to analyze the algorithm. So the crucial fact is we're not using the LP in the algorithm. It is just in the analysis part. And slight difference in the analysis using weight function and duality is in the weight function, what we did is we look at every feasible bin and say their weight is less than U, and then sum over all items and we get opt times U. Here directly we get this fact that Wi by U is less than opt, but they're essentially same. So let's conclude now. We have seen this first fit algorithm, and we understood that if an item we are not able to put, then that infeasibility is giving us inequalities which will help us improving the guarantees. The weight function can be thought of a dual fitting certificate. And 17 by 10 weights that we saw, it has three parts. One is some baseline, there is some transfer bonus, which we're transferring from the item in the next bins. And for singleton items, we use some extra surcharge. And then we realize this function is not magical. The reason this 1/6, 1/3, half is appearing. There's a discontinuity at half. There is some slopes which are varying. All this comes quite naturally. Now there are several open questions. One is, are there better orderings or modification of first fit which can lead to a better practical algorithm? For example, first fit decreasing has guarantee of 1.22 and modified first fit has 1.18. Can we improve them using some other permutations? I mean, one candidate could be maybe instead of first fit decreasing, which always consider items in first fit decreasing one by one, but maybe we can do it alternatively. So we sort them and maybe pack large item, then small item, then the smallest item, then the next largest item, and then smallest item, or some other variants. It's not clear. So if there are some other simple variants, for example, even random permutation, I randomly permute the items and then run first fit. What is the guarantee in those cases? These things are quite wide open. And first fit shows a simple, not simple, but at least a nice application of weight function, but it can be quite tricky. For example, the analysis of first fit decreasing of 11 by 9 is quite long and intricate analysis. And these weight functions are also used in online bin packing for harmonic rounding and other algorithms. So we still don't understand the power of weight functions completely. So what is the best weight functions we can have for any online bin packing algorithm? That's also not completely clear. So there are several nice open questions in this. Please write in the comments if you have any other questions or any other comments about this lecture. Thank you.